Chapter 15 is where we'll begin, and this is all about wave motion, in particular traveling waves. If you want an idea of waves, the sort of thing we'll be looking at, you can think about waves rolling in on a beach like this. People who live in the St. John's area might actually recognize this. It's a little clip I took when we went down to Bay Bulls one afternoon. So this is what we're going to look at when we talk about waves, this kind of motion. Ways we'll characterize waves is we'll talk about how fast do they move, how high are they, how far apart are the crests or the high points, and how much energy is transferred as they move. For a motivation, you might ask, why do we study waves? And the answer is wave motion is all around us, particularly in light and sound. Both of those things are actually waves. It's how we take in information about the world around us. Therefore, it's really important to understand waves. When we talk about waves, I'm going to say that what we see here in this video is one of the first things that pops into my mind. Can you see it traveling? Now, that's called the wave. Your book talks about the wave in this chapter, and your book comes to the conclusion that the wave truly is a mechanical wave. I disagree with your textbook. I would not call this a wave. So I'm going to invite you, as we go through this chapter, to draw your own conclusions. Do you agree that it's a wave, or do you disagree that it's a wave? You might want to pop over to the discussion group and put your thoughts out there, and maybe see what the rest of your classmates think about. So what is a wave? Let's look at the familiar example of a wave in water. What I have open here on the screen is a PhET simulation about waves. I'll click play and we'll just watch a water wave. So we drop the water in and you see a disturbance spreads throughout the water, a ripple spreads. So there's the top view. We can also do the side view. So the water drops down and that ripple spreads throughout the surface of the water. This is a wave or a traveling wave. Our next questions will be, what is a wave? Kind of what exactly is moving and how is it moving? Let's start with some definitions now. What is a wave? Well, a traveling wave is an organized disturbance traveling through a medium with a well-defined speed. Okay, what about this word disturbance? What does that mean? So let's think about the water wave that we saw either on the simulation on the previous page, or the water wave you might see if you drop a rock in a pond. So if you drop a rock in a pond here, you'll see those ripples spread outwards. The disturbance is the ripples. So in our water wave here, we see it spreading out because these ripples spread out. In a water wave, the disturbance is those ripples. Okay, the traveling wave travels through a medium. What do we mean by a medium? The medium is the substance through or along which the wave moves. In the case of a water wave, the water is the medium. So what happens in a water wave, and I'll just kind of draw it here, the ripples travel out over time. And they disturb the water because the water goes up and down. So first one part goes up, then it falls down, then the next part goes up and it falls down. The next part goes up, falls down, and so on. So each little bit of the water goes up and comes back down. So that's what happens in the water. The water itself doesn't really go anywhere horizontally. It moves up and down a little bit for a while, but it doesn't transfer from one side of the pond to the other. But the traveling wave is a disturbance that travels. So what thing is it that's moving? Well, if you want to understand that, think about if you're standing on a beach and a great big wave comes in and hits you. what happens? You probably fall down. That's because that wave contains a lot of energy. So the disturbance that's traveling is actually energy. Energy is the thing that's moving through the wave. So energy is the thing that's transferred in a wave. So there's a definition of waves. There are two kinds of waves, and we'll discuss both in this course. The two kinds of waves are mechanical and electromagnetic. Mechanical waves, like water waves, they move through and disturb a medium. So they propagate through and disturb a medium. Examples are sound waves and water waves. You have to have some sort of source that starts the wave, and the wave propagates, it moves along by some physical interaction between the elements of the medium. So one bit of water pushes on the next bit of water. The elements of the medium each move, and the collective movement of those elements is what makes the wave travel. So for example, if you shake a string to make a wave, the wave moves through the string and the tension propagates it along. The other kind of waves, and we won't go into details on those in this chapter, but we will come back around to it, are electromagnetic waves. They travel without a medium. And we know that's true because light gets here from the sun, so it has to travel through space. Electromagnetic waves are actually oscillations of electromagnetic fields. That's really cool, and that'll be discussed in the last part of this course. There is energy transferred in an electromagnetic wave, just like a mechanical wave, and we know that's true because we feel the heat from the sun, which travels through space. There are three kinds of mechanical waves, and I'm going to try and show them to you with a slinky. So the first is called a transverse wave. So I just have a slinky here. By all means, try this at home. If I spread out my slinky a little bit and I just push up at one end. So I push up, you see a wave travels down the one end and then comes back. What happens is that the elements of the medium, that's the coils of the slinky, they each pull up and down on the neighbor. So this pulls on its neighbor, which pulls on its neighbor, and that's what makes the wave move. Overall, the slinky doesn't go anywhere, but the wave does. Okay, the next kind of wave is called longitudinal. So if you can see, I'm pulling a couple of coils together, and I'm going to let it go. So that's still a wave, so I pull some together, I let it go. The thing that travels here is the compression. So sometimes they're compressed, sometimes they're spread out. And in that fashion, the elements of the medium interact by alternating compressing and relaxing, and the wave moves down even though the slinky doesn't go anywhere. The third kind of a wave, I can't really show you on my slinky. It's a combination wave. It has features of both transverse and longitudinal, and we see that in water waves. For mechanical waves, there are three different types. There are transverse mechanical waves, longitudinal mechanical waves, and then combinations. So in our picture here, we have a hand. That's the source of the wave. So you flick one end of your rope or your slinky up, and then your wave is the disturbance. So this is the wave itself. And that wave, that bump, that disturbance, that travels along the rope with a speed v. So that's the speed at which the disturbance travels. If you had a meter stick and a stopwatch, you could measure v. You could see how far your disturbance traveled, and you could see how long it took. You do distance over time, and that would give you that wave speed. When we talk about a disturbance, what exactly do we mean by that? Well, if we look at our wave, we see that the wave is disturbed from equilibrium. So the straight part of the string is in equilibrium. That's at rest. It's not doing anything. And the disturbance of the wave, we see the bump goes up. That's disturbed. It's different from the equilibrium. So that's what our disturbance is relative to some equilibrium value. For our transverse wave, and that's the kind we see on our picture here, we see that the bits of string go up and down. Bits of string is what we call the element of the medium. So an element of a medium is a piece of the medium. Each piece of our string goes up and down while the wave goes to the right. So for transverse waves, the elements of the medium move perpendicular to the disturbance. And that would be waves on strings as an example. For longitudinal waves, that's the kind of wave we saw in the video where I compressed a few coils of a slinky and let it go. Longitudinal waves have the coils of slinky relaxing and compressing alternately. So the elements of the medium move back and forth, but the wave itself moves forward. So for a longitudinal wave, the elements of the medium move parallel to the disturbance. Waves on a slinky are one example. Sound waves in the air are another example. The equilibrium condition for waves on a slinky, for example, would just be the relaxed slinky. Our combination waves have both kinds of motion. The elements move both perpendicular to the disturbance and parallel to the disturbance. An example of that is actually water waves. Water waves are super cool and they're kind of really interesting to study. We won't go into any details about this in this course because it's just a step above where we want to be, but it is super duper interesting. You might like an oceanography course if you find this cool. So the equilibrium state for a water wave would be the relaxed water. We start a wave by inputting some energy. Say we just give the water a shove with our hand. And the energy travels along the medium because each little bit of water pushes on the next bit. So some of the water goes back and forth, some of the water goes up and down, and in fact what we see overall is that the water tends to go in a circular motion on the surface. So it does move both ways. That's pretty nifty, but like I said, we won't do an awful lot of that. So what I said here, that the wave propagates because each bit of water pushes on the next bit, maybe I'll just leave that as a hint as to why I don't actually believe the wave is truly a mechanical wave. So I'll ask you to draw your own conclusions. Do you agree or disagree with me? And maybe go have a chat about it in the discussion group with your classmates.